seminars will start soon after my small talk. So dear all, welcome to the lecture rather than seminar series on reproducing kernel Hilbert spaces, simply RKHS and its applications, particularly in machine learning. We wish to thank, first of all, Bülent Karasözen for bringing this topic into our attention and awareness that without his and Professor Aydın Aytun's generous attempts in organizing such a lecture series, hopefully we will all enjoy and try to learn the topic and hear later on from specialists and experts on the possible applications, preferably on machine learning and further analysis of RKHS. As of today, we will be starting the journey in learning and collaboration if possible. This lecture series is indeed divided into two parts. The first one is learning seminars and the second one is expert talks, which might be considered as regular seminars, by the way. In learning seminars, better to name it learning lectures, we will be introducing the topic and, most importantly, learning the fundamental tools to better understand RKHS and its applications. As you might have inferred from the title, titles of these starting talks on the website. On my side, I'm not an expert, nor do I know the topic sound enough. Hence, my talk will be too basic. However, I must admit that RKHS is a very much appropriate and appreciated space in many applications that we have been doing for years without putting them into a sound theoretical framework, which is the RKHS. Having equipped ourselves with the necessary tools, hopefully, in the second part of these seminars, we will try to invite experts, both in theory and in application of the RKHS, particularly in machine learning. And hopefully, with these lectures, we will get to know each other and each other's interest in the topic for further collaboration of any sort. We may well advise a student or participate in a project or even keep learning for fun, as I do in most cases. Well, today our first speaker, Professor Bülent Karasözen, will start this seminar series with a talk entitled Kernels and the RKHS to introduce us to the topic and its applications in machine learning. For those who don't know Professor Karasözen, he is one of the founders and the directors of the Institute of Applied Mathematics. In parentheses, we really appreciate the Institute of Applied Mathematics for giving us this opportunity. And this is a nice event for this institute. Although Bülent Karasözen is retired, he has never given up working and advising many students.
Good.
For further details, please find the website of Bülent Karasözen, and you will get to know him much better than what I told, because if I start talking about Bülent Karasözen, I have a 30-year background with him.
So look at the Google Scholar.
Yeah, Google Scholar, or just search on Google.
Google
Okay.
Scholar page.
Before I invite Professor Bülent Karasözen for his talk, I would like to ask if anybody has something to say, maybe about the expectations. Possibly we may start with Professor Aydın Aytun, another founder of and also the first director of the Institute, about the seminar or lecture series. Would you like to add anything, Aydın Hocam?
No. Let's get started.
Okay, if there is anybody else who wish to talk, so there is a chat, which I can, oh, not chat. Okay. Okay, now let's get started. Therefore, we thank Professor Karasözen a lot, not only for what he is meant for us, but also for starting this lecture series. Now we invite him to give his talk on kernels and RKHS. So let's gear up. I share. Okay, you may start, Bülent Hocam, if you have the control. If you don't have the control, please ask for the control once again.
Control again, okay. Control, request, okay. I have requested control. Let's see now.
Okay, I have given the control for you.
Recording'i kapattım. Okay, bakayım iniyor mu? Daha kontrol almadı ama. Dur bakayım. Control request yaptım ama.
Almış hocam.
Almış mı? Yani, tamam. Okay, let me say a little bit about the history of the Institute, especially Scientific Computing Research Group and Scientific Computing Program. As we started in 2002 with the Institute, before we made a lot of search and we had some international congresses, and then we oriented in scientific ourselves to the SIMES report, Society of Industrial and Applied Mathematics. And in this report in 2000, this was emphasized now more computational science and engineering, like simulation with finite elements, maybe human body, or let me say then another here, finite volumes and in the industry, and then etc. A lot of problems. That was now the state at that moment. And then, as you know, here then some people gave here lectures about here, for example, simulation with the key operations with finiteism, etc. And after 2000 years, last year, I was operated with Enchanka Hastanesi, about the hospital with robots, and this is an implemented finite element here techniques. And you see now we want to show now how the mathematics now impacts industry and applications and all the engineering and other fields, etc. But now the screen is changed after 20 years. In 2020, SIME published another report and then emphasizing data science. What is the data science? Data science now is a synonym for machine learning, deep learning, or let me say commonly now is artificial intelligence, on the statistical learning, etc. All the techniques. What is the behind this is, you know, is a huge amount of data available worldwide now. For example, from the seismology, you have a huge amount of data, and then you have now from the Facebook a lot of data, finance data, etc. And then one needs now new techniques to handle this huge amount of the data. And this is now and then for this purposes now new techniques from mathematics now appeared. And one of them is now the RKS, I will now introduce today here. And then especially the linear algebra become very, very important for numerical applications. And before 20 years ago, it was not so. But now with the emergence of the data science in the last 2 decades, linear algebra became very, very important in many applications. Today, I will give now some introductory examples and what kernels are and how they are related to the theory of the RKHS, but I will not go in the details because they will give it now about subsequent lectures with the proofs, etc., and why important this. So kernels and then RKHS. What is a kernel? Bir dakika inemedim ben. So you look at now this picture. This is here this XOR gate. On this is then typical here logical command either or, true, false, etc. And then what's in here in the 4 cases they can be switched. When you now apply to some here data points, and you will obtain here such a here. On the left here, you get here now 4 here, let me say clusters, and then red and then blue, and you cannot separate by a linear classifier. It's impossible. But when you now go with a feature in a future space with a nonlinear mapping from x1, x2, and another coordinate x1, x2, very simple, R2, and then you see this is not clearly separable with this plane. And that is here now the feature mapping, and the kernel is defined, and that is this is the idea. Going to the higher dimensional space, what we cannot do in the original space, we can do in the future space. And the nice thing is that everything you can apply here in the original space with the linear algebra, you can apply here with the linear algebra techniques too. And I will give now more and more examples about this. And then when we now go, let me see now then. Maybe it was too short. Okay. Okay. And motivating and bir dakika. Biraz hızlı gittim herhalde. Dur bakayım. Buradan çok hızlı gidiyor. Kontrolle yapamıyorum da. Tamam, çıktı yukarı. Okay, this is now the RKHS. No. Okay. Okay. Okay, then maybe next picture. Okay. Yeah, this is the many algorithms is called now, for example, support vector machines, and there's classification or principal component analysis. So let me say the model order reduction. And then another here area is now the machine learning similarity measure between the two distance points. When you now have a dot product, you see now the angle between now the here two vectors or the distance, etc., gives similarity or dissimilarity. But they can be now exemplified, or then that they can be now better now computed using the kernels in a future space. And then there are many, and this is interesting, this is now not only now the real valued vectors are using kernels, and there will be now here a lot of other here, let me say, different kind of here mathematical objects like graphs or strings can be used with the kernels can be designed. That is not only restricted to the Rn, so that let me say. And then I will show at the end some examples. There are a lot of here now work with the graph kernels on the deep learning. Okay, learning is defined. So, for example, and this is very interesting, not between the features is within the kernel, and this is a kernel trick. When you now click on the Google kernel trick, you see several examples, which simplifies a lot now the computation I will show. And then kernel is similarly refers to the dot product between the features, and there will be now finite or infinitely many features. And then kernel methods can be viewed as a non-linear version of linear algorithms, but the linear, then applying the linear algebra in the kernelized version, in the kernelized form. Okay. Okay, let me show you a simple example, because I will not talk about the support vector machine for classification. I will give another example a little bit in detail, because it now requires optimization, etc. It will be involved a little bit. And in the lecture, I left it here. And you see, this is a typical here classification. And you can classify the here, you see now in the left here, you see, and this is a nonlinear classification with an ellipse here. But here is a classification in the future space within a linear space. And this is now a lot of techniques. Support vector machines is really very important for many classification problems. And there are a lot of books here on this and softwares, etc. At the end, I will now explain it. Maybe in our lectures here in the statistical learning and simulation, I think we give some introduction, or let me say in optimization lectures. It's a constraint optimization problem. I will not go into details of this here in this lecture. And another one is, which I will now talk a little bit about it here, the regularization technique. This is typical least squares here problem. And you have now, for example, here some dots here, some measurements, and then you want to have a here parabola here. So, or you have done, let me say, and you want to fit here, this is so-called now the so-called underfitting, because the errors are very large. But when you now hear the fit exactly, that will be the overfitting. This is the main problem in all deep learning problems, because the data is trained too much. And then when you have a new test problem here, and it doesn't work. And this is one of the problems here. Or you can choose the parameters so optimally, and you have a compromise between them, and then you have now, let me say, a simple, better least square problem. And then I will give the definition of the kernel. This typical regularization problem is called rich regression, and then use a Tikhanov regularization, and it's very common in inverse problems everywhere. And then use this as a regularized version of the least squares problem. Okay, Hilbert spaces and then RKS. You know, the Hilbert space is very simple defined here is over the dot product here, and then inner product is defined with this here using this here definitions like this here, and that's, as you know, everybody knows here the definitions, I think, and then you define a norm. And then this is the inner product space. The Hilbert space is defined with the inner product along with the condition that it contains all the limits of the Cauchy sequences of the functions. I will go now on all the details and then all other things. That is now the basis of the here. And the RKS now built on the kernels of the Hilbert space, simply said. Okay. And you let me give here, that is the important, when we have here kernel is defined from two set of here to a non-empty set as a mapping to the R. When there is here a mapping, it's a so-called feature mapping, that the dot product of the feature mapping in the Hilbert space is the kernel. I will give some later on definitions of them. All kernel functions are positive definite. You can give the proof. And then if we have a positive definite function, we know there exists one or more future spaces, and future spaces are not unique. I'll give an example, but the kernel is unique, and defines in the here a kernel kernel. Then this is now a positive definite functions of kernel given in that form. It is a condition. As typical condition here, kernel is positive definite. It's a symmetric here, kernel. And then you can build a matrix. I will later on show this is called gram matrix or Gramian, etc. in the kernel literature. And strictly positive definite when they are distinct for mutual xi. For example, not all the kernels are strictly positive definite. For example, polynomial kernels are positive definite, but not strictly definite. I will give examples then. Okay. And there is here is very simple. Then you can sum the kernels is again kernel, but the difference should be not negative, and then is not a kernel, because kernels are positive definite. The difference will be should be not negative, then it will be not a kernel. And then you can get product of the kernels as again kernels when you have on the same here set, and you have the square of the kernel or the product of the kernel, etc. But I think this is now very simple to prove, etc. It's very simple. And then let me show now then. Given now some examples, there are a lot of kernels. You can find the list, and it's depending on the purpose and what you want to do. And this is typical is now the polynomial kernels. For example, x, x dot plus a constant to the power m is positive number here. When m equal than 1 is a linear kernel. And then exponential kernels, there are a lot of exponential kernels, and then with the one norm, etc. But now, one here, the most famous kernel is the Gaussian kernel. A lot of here very nice features, and this is used very often in the because now you can hear now a lot of here probabilistic interpretations, etc. And there is a lot of here properties of the kernels one need now in applications. For example, the Gaussian kernel is translation invariant. When you shift, this is now then invariant. It's important for many purposes. At the same time, it's symmetric. And when we use, for example, when you now have data for Hamiltonian systems, that's important that you have now the Gaussian kernel, which is and then invariant. And I said now the feature maps are not unique, and the kernels are unique. I gave an example here, very simple. You have this kernel, but you can now define two feature maps, different, giving the same kernel. Okay, that's only now to show you that the feature maps can be defined differently, but we never work with the feature maps in the computation. We work in the kernels. I will show them later on. Okay, that's now important. Okay, then coming now to RKS, and this is now, I will show now the Aronosian's theorem, 1950s, and that is typical in pure mathematics now. That's now then appeared as a let me say, nice article, but there were no applications, and then after 50 years, and this is now at becomes now became very important. So that is you have really instead of the dot product here now we have then a kernel in the Hilbert space, and then you have now defined then with the function and then a kernel in the Hilbert space the dot product, and that is fx, this reproducing property, and this is the Ritz representation theorem in the functional. Is nothing else then. So that means you can now define the function in the kernel space, taking now the product in a product in the Hilbert space, and then we will see now a lot of examples. That is now the converse holds true when you have now the representation. Then it is now is the RKS, and then they will be now here. I think will be defined later on more in detail. And to show you here now that when you have now two functions and they are now given a linear combination of the finite, maybe then infinitely, I don't give them infinite now, then kernels, and then you have the sum, and then both are in the Hilbert space, and then you can have now let me say inner product of them, and this is then K is then unique reproducing kernel on the Hilbert space in positive definite kernel. This is a theorem of Aronosian. And then I show you now here very simple now the picture here where you see now how this is mapped here from the R to the Hilbert space. This is not more on the Hilbert spaces, that means RKS, and defined more in detail and using now all the properties of the Hilbert space. So that let me say that is then in the function spaces, the RKS is very small on the Hilbert space. Let me embed it on the Banach space and Hilbert space, vector spaces, Banach space, Hilbert space, and then RKS in this here picture. Okay, I said now here a little bit about this kernel trick. And it is not so that you have only always the points. Usually you have now the vectors. Why do you have vectors? For example, when you simulate the data, let me say now then turbulent flow, and you get experimental data, and for each time instance, you have a vector, let me say with 1,000 components or then 10,000 components or seismic data, etc. And then you have to work with vector valued RKS. And then it is important that you have, because now the vectors computation will be very complicated, and if you have something like this separable kernel, so that you have now here, and each now here between 2 points now, let me say the kernel, and multiplied with the identity vector, or you have a tensor product of them, and this simplifies now all the computations. For example, Gaussian kernel is a separable kernel. And let me show you a simple example with the kernel trick you can find everywhere. You have, for example, we have a polynomial kernel, and then with the mapping, 1 plus x transpose y, p, let me say, this inner product here requires of order n operation. Consider the length of the axis that is then n. Then when you take then n operation, then you take now you get a number and then take the square of this. Is very simple. But when you want to now write is a feature mapping, and then try to find now the product of the feature mapping with the transpose with this here, and then you need enough operations with this here binomial presentation. For example, when let me see P with 20, and then you have n vector length n 3 times 10 to the power 22 operations instead of 100 operations. This is the kernel thing. Everything is done in using the kernels computations in the dot product in the kernel with the kernel, not with the feature mapping. Okay. Okay, maybe a little bit about the smoothness, and I will now introduce with this the concept of the distance between the kernels. Everybody knows, and this is with the Cauchy-Schwarz inequality, and then the difference, difference between two functions, functions with 2 points can be written in that form, and you then apply then the Cauchy-Schwarz inequality, and you will get now the norm of the Hilbert space and the distance between the points here, and the distance is defined in the future space or with the kernel, and you have a kernel x1, x2 plus kx, x2, x2, and then minus 2 times x1 and x2. This can be now computed very easily. And the smoothness is very important in applications with the kernels here. And when the Lipschitz constant, that is the Lipschitz constant f of x, the Lipschitz constant small, that means small variations of the function. And I will show at the end of the with the regression why this is important. So machine learning applications, I will give only 2 applications a little bit in detail, but not too much, because that takes a lot of here than time. And that's the first one is now the class. The first one is the principal component. Principal component analysis is the following. Now, when you have a huge amount of the data, and then only the few here components of the data is relevant, important. Let me say 3, 4 components, but not the most of them are don't contribute too much for the significance of the data. And it is important to now to extract now the here this directions or this mapping, this here the features. And this is simple as is a optimization problem here, and you have here the data points xi and then xi, and then you take now the with ut u object that should be now then okay. You can define this is principal components here, and then you can find now using the Gram matrix here in that form, and then with the covariance matrix you can find now this is an eigenvalue problem at the end. And then these gamma i's are the principal directions, ui's the principal vectors, and this is now the covariance matrix. This is very common here, and this principal matrix is here to give now the directions. I will show you now the next example in a future, and here you see now. Yeah, for example, you have such a scattered data, and you see the data is the principal component in this direction, one of them, and the others are smaller of size, etc. And PCA used very often in medical science, and it's because now we have a lot of your data, and then you want to reduce the dimension and model order applications, etc. It's one of the typical machine learning here concepts or then tools. And now, how can we now do the same? Here we can go and when we go now to the kernel version, and then we have the same one. Now instead of the here then data points, we have the feature mapping, and you see here now the from the RKS very simple now the dot product, and here now the feature maps here now, and one of them is in kernelized version here. And instead of this, you can take the variation over F, smoothness of this variation of F, and the covariance matrix will be a little bit technical now. This is product here, here like a tensor product here, and you have instead of this here, you have now the kernelized version and nothing else. So, Okay, so the same techniques as you have in Rn, and when you're going to future space, you have then the kernel principal component. You have the same, and this is more powerful than the usual. What you cannot do, for example, the principal components in Rn, and you can do in future space, possibly. It's very simple in a here application. For example, is here PCA used by face recognition when you now go to another country on the borders and your here picture is there is recognized. And when you look in Netflix now, there are a lot of here in criminal data, and that's automatically now recognize the feature, the faces, etc. And they use now the kernel principal component analysis or principal component. And you see, and the digits here, this is now the here down. Then you use this typically here now. Then you have these digits, and that's then add noises of them. And then you can apply normal PCA, linear PCA. But when you apply kernel PCA with the Gaussian kernels, and you see that the contrast is better. So that's now the simple. And with a little bit computation, not too much. So this is, you see now the power of this here than PCA. Okay, then let me go now then. Is now the ridge regression. Maybe ridge regression important. I will show later in the example here. And when you have the data, I show it at the beginning of this here, this three curves with the underfitting, overfitting, and normal fitting. And when you have here, you have now, let me say, the points, and then according to this some data, for example, let me say, every day you take here some. Maybe these are days, and this is your body temperature or something like this. And you want to fit them with your curve. What will be the simple curve? Let me say parabola, maybe then cubic function, etc. But usually, only doing this in that form, you will never get, let me say, good results. But instead of regularize this with some lambda and with the 2 norm here, and this is a called famous Tikhanov regularization and used everywhere in on inverse problems here, and you can take other norms to 1 norm, etc. But it's a simple this one here, and then you will get now the regularized least square problem here. And the regularized least square problem here, I will show what the x data is then here. You can find the solution. This is really a hard problem because it is now X is very large matrix, and then X transport that will be very large. That will be ill conditioning, so that means there will be a lot of noise. And this is one of the most important here tools or then methods of the linear algebra is a singular value decomposition tool. Singular value decomposition, eigenvalue decomposition, the square of the eigenvalues here, and they are decreasing. And then when they are decreasing to 0, and you take now the only, let me say, but kernel PCA and PCA, only let me say 10 most important singular value. You get a threshold and take only this, and you have a small amount of data. And then the rest is not important. Okay, and we use very often, for example, for Mulder or reduction on all these applications. SVD is the really workhorse for all linear algebra problems here. And this is now here a little bit, and the kernelized version is the same again. Instead of then, yes, you have the feature mappings between them, and then it is important. Then X plus X transpose is then is now given in the form of the let me say kernels, but instead of this, you see you can write direct as a kernel matrix in formulas. You don't need all this here, the feature map. This kernel, this is the so-called cram matrix. And then you take now, instead of then X transpose X in linear version, then evaluate the singular value division in the kernel. But the dimension is very high. It can be high. So, and this unit may be then more powerful here, singular value decomposition, for example. And this is open now new here research directions like this for the computational efficiency, randomized linear algebra, etc., etc. And this is a lot of techniques. I will not go this in the details when somebody working and then use now these concepts. Okay, now let me show you, and in the rich regression, we had two parameters. One parameter is, now then we fix now, for example, we use the Gaussian kernel, and we fix now in the Gaussian kernel, in the denominator this here, parameter sigma, and we fix this to 0.6, and then vary the Tikhonov parameter. And then when we use here very large Tikhonov parameter, we have not good results. When we use too small parameter, this is underfitting, this overfitting, and we fit the data, but you see that's physically is not so good because this doesn't mean too much. This is overfitting. But when we choose another here one, let me say, we get here now the better result. And then because there are two parameters here, and then instead of then you can use, for example, here take now now you can then vary instead of this here now the in the Gaussian kernel now the parameter and fix now the Tikhonov regulation you can get. It's used very often. For example, it's used in the inverse problems. Now, as you know, my daughter SK is now studied now and working in the seismology, and they are now trying to find is the landslide in the Illich. Now the forcing acting on the sear, and then they have the seismic data, and they integrate it, and then use now the inverse problems, and in order to find now the forcing history of the data, and then use some here the Tikhonov regularization is everywhere. In the inverse problem we use everywhere, in medical imagining everywhere now uses here the data. Okay, let me say. Okay, these are now this is the explanation of this about it here now, let me say, and then how to apply the regression. You may say now, how can I find this here? Automatically there are here some techniques, and this is the so-called, what is done here, then M-fold cross validation program here, and you have the training tests, and then vary a lot of with the training sets, and you can choose now the optimal values. And this is typical here now, let me say, artificial intelligence and machine learning problem. And when you now in the training sets fix the parameters, and for the test sets, you use now test cases, then you use the same parameter. You cannot invite the parameters again. There's a training. And when you train the sear curves and you see, and you have a similar data, and then, for example, we have now the earthquake data about this here next Kahramanmaraş earthquake, and we have all the data and train, and then make a model, and then when in the same area, and we have a new here seismic recording, and it comes now, and when we apply to this, maybe we can make early warning, and then you can taking the training data, and therefore. The mathematics now plays an important role. They should be robust, and this is important by recognizing the pictures, etc., and use a lot of here by medical imagining, because they have thousands and 10,000s of tumors, and then when a new tumor appears now, they should be recognized, and then all here in medicine used very very often now at the moment here, and therefore should be used, and there. Especially in the deep learning, this is now the here perceptors here, use 1,000, 10,000, 100,000 of parameters. Usually people don't know how the parameters are defined, etc., what is behind it. And therefore, so a lot of more mathematics needed. And this is now the kernels are among them, not only, let me say, there are other techniques, but with the deep learning, let me say a little bit, in the deep learning, you go from one layer to the next layer, and some activation functions are used. They are all nonlinear. But when you kernelize the nonlinear functions, they are done linear. Then apply the linear algebra, and it's really powerful. So that's now, therefore, now the new kernels or kernel machines are used now for the deep learning, and maybe it will be better than the results with the other deep learning structures. And let me say a little bit here, real world applications. And I have taken from, there are a lot of here presentations and in YouTube, a lot of here explanations about the RKS machine learning. For example, the protein data, they look like the graphs, and they kernelize them, then predict what will be the next protein, etc., or something like drug targets and this and that of those. Because now the production of a new drug is very costly, because you try many here drugs, etc. Instead of that, when you know such techniques, you can here save a lot of time and then a lot of money. And this is used very in the drug design, a lot of here mathematical techniques. And another here very simple one is a support vector machine. You want to now then classify and what are dogs, what are cats, etc., something like this. And this is now a simple then cat. This is used as a binary classification. It's called rich regression, but logistic, only 1 + 1 - 1. So cat or dog. Okay. And then maybe a structured output, because now ChatPy used now very often now here, and then the translation. And this is typical here an example. And you want to produce a structured output. And the structured output, you can use all these letters here, and then the kernels can be used everywhere. You can now make kernels from the letters, or you can then design kernels from the books and from the chapters, etc. This is free. So I've tried now to give a little bit now overview over all this, but I will not, because we have enough time to go now in the details, because it's not necessary. And then, but my advice is now, first of all, people who are working with this, especially students, should be acquainted with the linear algebra techniques and what are now these techniques, machine learning techniques in RN, and then they are then use now them, let me say, in kernelized version, and that's very straightforward. It's not, let me say, very some new techniques, and the theory behind it, functional, is important. In many cases, only the definition of RKS is enough, but not always. For example, I am working with the linearization technique is not linearization, reduced order modeling with dynamic multi-composition or Kopman analysis dating back 1930s, and there are here some problems, especially with the Kopman analysis here with the RKS, theoretical problems, because the Kopman operators are not closed under the RKS, and they can be here, the results can be now sometimes false. There is not founded, so let me say, mathematically. There will be now really need to hear more theory, and then support from the theory. Not only them, most of the time, let me say, the machine learning aspects. So I have now here many of the here give some lecture series by Arthur Gretton here, and there is here by in London in a university is a works in neuroscience and biomedical science, a mathematician, and he had a nice here small lectures. I have some taken all of them, but was no book. And there is another here the kernel course, but the second one is now only here a huge PDF file. You cannot get too much, but by Groton has a lot of here notes, etc., and a very simple introduction by avoiding now the details of the theory. And then there are here a lot of here codes, especially now the by support vector machines, as called the CodePy is a Python code, or by scikit-learn here. There's a Python code, and nowadays is popular now. Every paper in scientific computing now gives the software or the package or the programs used freely, and then you can have all the problems and then run. And then there are a lot of here, you can find everything. And many people now supply with, let me say, the paper and then YouTube presentation of the paper. So, and then a lot of here, when you are interested, I can give this, so you can learn, you can read the paper, and then participate now to YouTube and then look at now how this works, and then run the program, and then in order to understand. This is now the common in scientific computing. And about the references, I gave only now the, let me say, the books, because the literature is very rich. I think approximately, let me say, around 100 papers now in mathematical papers appearing now every year on RKS, and with the different aspects here. And this is now here, this is the dimension reduction, so-called manifold learning, so non-linear learning, not in the space here. And then a primer, and Ömer will talk about some chapters, and as you said. And then Paulson is more theoretical, and then Preserve, then I think that is, and let me be more artificial intelligence. You have to look the books now, because every author has his preferences or her preferences, and then and there is here now then about let me say vector valued kernels, and then maybe there's a Sherlock's here book is now, let me say, appeared to 2002. This is the one of the fundamental here books here about this. This is now the learning with kernels, support vector machine, regularization, etc. Everything appeared there in 2002. It's still very popular, and you can find almost everything, and people refer too much to this book here. And there is another one, Japanese, but it's kind of let me say it's preference, and there is a feature learning, understanding algorithms, applications, a lot of other things. For example, you can find there about signal processing, maybe interesting for electrical engineering, instead of Fourier transformation and then wavelet transformation, and going down to the kernels and then apply the techniques. They are not used very much when you have the applications, and then you can use the techniques, a lot of here, and then go to understand all this paper. So yes, see, this is really a wide spectrum of here research possibilities are from the programming, and then maybe for thesis and so as understanding. But my suggestion is cooperation, and this is cannot be done with one or two advisors, and then one is with cooperation, and maybe then concentrating about some here topics, and then the institute can make impact in this area. And this is used here, for example, this one of the CodePy in financial applications a lot. For example, I don't know in cryptology, but now I think scientific computing and mathematical finance, and then acquired sciences, because a lot of data, they can work together. So this is, I think, a lot of things. Because I said, so this situation is changed now after 20 years, so that the data science is dominating, and I suggest the institute should emphasize and design or redesign the lectures according to the data science. Okay, thanks a lot. Okay, so, I'm done.
Thank you. Thank you very much, Bülent Hocam. If there is any comments and questions for the first seminar given by Bülent Hoca.
I have all the books, because I cannot because we cannot book on the web, because this is of the copyright restrictions. But when you're interested, you write to me, and I can send you. This is no problem, because all the books will be Google Drive, etc. when you are interested.
So some of the books can be found using Springer link, I guess, if they are published by Springer anyway. If they use Meta accounts, because Meta IPs are defined, so some of the books can be found. And also we try to give the DOI numbers on our websites. Please check the website for possible links for those books, if there is any.
Maybe it will be interesting now. It will be useful when you now have to give websites of the conference. I can provide some of them when students are interested. Also now to all the websites and then some YouTube presentations, etc. But you have to be careful about using the books. And first of all, read, and then you see whether this is now is for proper for your purposes or not, because it's different. For example, the Suzuki book is a little bit strange. This is here now his his point of view is nice, but when you read it, stick on this, you cannot do anything else. So, but you look now, it's, let me say, different here than choices. There are a lot here. But this is enough literature. Even then, you now click on, then you get on the website. And in Wikipedia, RKHS is now very finely described, and you can find everything. The occupation of the RKHS and then kernels as a very concise description of the theory, and then on all the kernels and applications, etc.
Okay, dear audience, is there any comments and suggestions for these series of seminars or lectures? Then we can talk a little bit more, maybe if there is nobody here who doesn't know English or who doesn't know Turkish, so we can also keep Turkish as our mother tongue after I stop recording anyway.
My suggestion for the courses now, maybe one or two here core courses on the data science. In the first, maybe on all the techniques of the machine learning. In the second course, more the advanced, like let me kernels and other things, etc. And then and this will be now here, especially very useful now for scientific computing, and then for let me say, and for the university too. And for instead of now taking now, let me say, courses then like a dynamical systems, etc. Students from engineering, and they can take now this data science courses, and then understand the mathematics behind the data science, not only then run the programs and then software packages and get this and this, and change the parameters, and then instead of this, they may think more about mathematics, and that will be now one of the tasks for the institute. And what this was now our purpose now, when we now here now then founded this institute, now to give them then mathematical techniques, make available, and then involve more people. They have to bring their problems and then work together. I think that will be a platform for not only for math students from our department, math department, institute, and then from engineering too, and biology or finance, etc.
May I make a comment? Can you hear me?
Yes, yes.
Yes, first of all, I'm very happy to see all of you. And I'm not an expert for the support vector methods, but maybe a little bit for the perceptron learning. And of course, the question is, I studied that other methods theoretically and also from the practical aspect. And there appear, Bülent Hoca has mentioned it, the learning rate, for example, and also the problem how to control the learning rate. It is always practically a problem if you want to have a robust application, and also to control when your algorithm is really finished, when your learning is finished. And so one question is, I think, also to see now in these kernel methods. So maybe some of you has already some answer to which extent also the same problems appear, and or to which extent they can be solved better. And actually, a question which I have in addition comes, if I see these methods, so from the functional analytical expansion in the function space, I have to be rigorous exact. I have, of course, to do expansion up to infinity, and also the problem where I can put the truncation. So up to which length or up to which order I have to do the expansion in function space in a practical problem, because in practical application also the time the algorithm is running is critical, particularly if I go to implement industrial applications, for example, in finance or other topics. It is very crucial, I mean, to know that the algorithm is finished in a definite number of microseconds or maybe fractions of seconds. So thank you. Anybody?
I think industrial, industrial or practical applications will be can be discussed later on. But I think the purpose of these lectures will be now to introduce in simple examples and then advancing the methodologies for the machine learning and the mathematics behind them. Then later on, they can be applied with the algorithm, because it's now here a huge practical application in Department of Computer Engineering. There are here a lot of research and then courses on data science, but these are only this here. Machine learning algorithms are given automatically behind without now explaining too much and discussing and the mathematics behind them. That is our purpose is now then exemplify even in simple examples when they fail or when they success, and then go. Now, let me say, then use efficient techniques, and then later on, then you can apply then for in medicine, etc., in finance, etc. But that will be now should be now the position of the math or the Institute of Applied Mathematics, and then our colleagues are working with them together in math department.
Thank you, Martin. Is there any other questions or not? Aydın Hocam, would you like to add a couple of words? Maybe I can start and you can add further. Thank you very much, Bülent Hocam.
Maybe may I ask to the students, how many of them heard about the kernels? Artificial intelligence, machine learning, they heard. Or how many of them heard about this now this year? It's like the regression, principal component analysis, support vector machines, etc. I don't know, because it's now they will show now the interest on this here later on. Because I said we need students when we work, when we want to make research on this topic. We need students, and okay. Important. They can now here understand the mathematics behind them, and then skillfully now write programs. And that is the most important thing.
Maybe I can add a couple of things, especially for the learning part, learning lectures of these seminar series, actually. Next week, I will start with linear algebra, by the way. So whatever you have seen today is a bit in the broad sense explained. So we will start with a simple linear algebra, how to define vectors, matrices, especially positive definite matrices, maybe. And we will also deal with a little bit in inner products. And maybe we will define again Hilbert space. And we will work on some overdetermined system and curve fitting, etc. Then we will go with the primer that we have already assigned or announced, a primer on reproducing kernel Hilbert space by Mountain and Amblad. So we will keep the first and the second chapter with me. It looks like it won't be enough to finish those things in 1 hour. So we will most probably take your time on Thursday as well. which we will announce that date, and also we will provide the link. I mean, the same link or similar link that you should participate online. And also later on, Aydın Hoca will take the job and we'll talk about, most importantly, the Hilbert spaces, and maybe to one of Martin's question is that when you have an infinite dimensional Hilbert space, and if it is separable, then you can have an approximation. That approximation converges. So it's a good one when you have an infinite dimensional Hilbert spaces, which can be approximated if it is separable. And that approximation will be good later on. But all those things will be given by Aydın Hoca on Hilbert spaces, and keeping in mind the RKHS. And most probably Aydın Hoca will also need not only 1 hour, but 2 or 3 hours for this learning seminars. So make sure that you keep checking the website for those announcements. And also, some of us would like to use the classroom instead of just virtual business. You may also come to the class, and maybe it can be more interactive. But of course, we will be online all the time. Whenever you see an online participation on the website, please self-register yourself and get the link to these meetings from the website. So I thank you all.
Ömer, a short note. Can you create a mailing list from all the participants when I want to send some material, or they will have asked questions and so on?
Yeah, we already have a Google form, and there are some emails of those registered ones, not to the teams for the meetings, but if they are interested, they have filled out a form, Google form on the website. So please try to fill that participation form so that we can send you emails whenever necessary. For instance, 2 days ago, I just used that form emails to send you a reminder for this meeting and provided the link for your self registration.
No, I mean not only now from the institute, because the people can interact each other now. So to have a mailing list or in a WhatsApp group or something like this here now, so we can now discuss maybe if some student or somebody interested and want to ask me or Aydın or you and etc. and then about it, and then we can now send messages, articles, etc., conference rules, etc. Not only this one, I think.
I don't know how can we do the mailing list, but
Set up
try.
With an assistant can arrange now all the lists, make a mailing list, and then that will now, and then we can participate with them or something like this. It will be not a big problem, I think. Up to you.
Yeah, if I just send all the emails to.
I really want to communicate with the people who want to apply, maybe engineers or mathematicians who are interested, or maybe from statistics or from probability theory, and a lot of aspects of probability, or for the students, maybe they want to write a thesis or something like this, and to know this is because a lot of here literature about is running. I have the papers, let me say at the moment here, about that, and a model or reduction about 10 or more papers with the RKS. I'm reading on alone now here, let me say. It will be nice to share with some other people and then see now what is the aspects, and I can explain them.
We have to think about those things. Maybe we can prepare a website or blog site for participating or communicating, because the virtual online business is a little bit boring, but this is the new era of online meetings, let's say.
Okay.
So do we have any questions or comments? If no, I will stop recording so we can discuss anything we like.
Okay, thanks a lot.
So thank you, and I'm stopping the recording.